Hello PCH Pre-Calc Honors. Welcome to your first video of the year here. So we're going to cover 1-1 and a little bit of 1-2 and then leave some for in class. And we're going to start off with a little bit of review back from Algebra 2, talk about what is a relation. So a relation, if you remember, is just basically a relationship between your x and your y. So it's a set of ordered pairs and no specific criteria. So we just have anytime any random x, y, that's going to be a relation. Now a function, on the other hand, is sort of a subset. So a function is a relation. However, it's a very specific type. It has restrictions. So each input, which is your x, so each input has a unique output, which would be the y value. So for instance, if you were given a table of values or a set of ordered pairs, you don't ever want to see a repeat in the x values having it go to a different y value. That's basically what you're looking for. So let's look at 3 examples. So here's 3 different ways potentially information could come to you, and then we'll look at it graphically. So we notice here we want to determine, is this a relation or is it a function? So what we notice is here at the number 2, that's our input, it's going to 2 different y values, so that makes this one a relation. And if you guys ever want to try and make the video a little more interactive, when we're doing the examples, feel free to kind of pause and try it on your own and then play back and see if you got it right. That's also a great way to see if you're understanding the concept as we go through this. Okay, on this next one, now we have a table of values, and again, for the input, here's a particular x that's going to -1, and here's a particular x that's going to +1, so that also is a relation. And then our last one here, we just look at the x value, 7, 5, 3, 1, 2. There's no repeat, so that means that every x value is going to a unique y value. Okay, awesome. Now a little bit of just terminology that might help as we are going forward. They have this, what is the argument of a function? So you know when you look at like f of x or sine x, when we're looking at functions, the argument is basically another way of saying what is the input. So in this case, it would be the x value. Then we have this concept of extrapolation and interpolation. I can never say that word right. You can read it. If you're given a set of data, what it means is extrapolation is when you are making a prediction that goes beyond, outside the given data, outside the given domain. If it is, so it's a prediction beyond the data. If it is interpolation, not quite sure the accent there, it's going to be within the given data. So it's a prediction based on, so it may not come from an actual data point that you're given, but it's within the domain of the given data. Domain of the given data. All right, and that's just because we are going to be looking at a lot of data in this class, a lot of number talks, and so sometimes it'll ask you to extrapolate something or look at something within the data. Now we get into probably one of the easier concepts, and also kind of a fun concept in terms of just ease of use, the vertical line test. So I hope you remember what the vertical line test. If not, remember, it tests very easily if you are given a graph, whether a graph is a function or a relation. Function or a relation. So the vertical line test is basically just that. If I draw vertical lines through my graph and I only hit one time the graph, then we know that graph is a function, because every x value corresponds to only one y value. So that's a function. Here we have a parabola, and obviously you don't actually have to physically draw the lines, you're just visually doing a vertical line test. That will be a function. As opposed to over here, if I do this, notice this particular x value is corresponding to 3 different y values. That means that's a relation. It's not a function. Okay? So that was it for 1-1. Pretty short. And we're just going to kind of review really quickly the types of functions we're going to be looking at in 1-2, and then we're going to save some of the more analytical stuff for when we're in class. So this first graph is one example of a polynomial, something I know you guys have worked with a lot last year. So you can see it has the general function with the decreasing, if you're in standard form, decreasing powers of x. The x-intercepts can be up to n intercepts. The turnarounds, which is another way of saying your max and your mins, so this is a turnaround, this is a turnaround, this is a turnaround, is always going to be one less than the degree of your function. So right now what we're looking at is a quartic function, and notice it has 3 turnarounds. The domain in general of a polynomial is all real numbers, and I represent that with the double sort of stem for the R. It's a short way of saying all real numbers. You're all welcome to write it out if you like. And the range kind of depends on what the function is. So we can't actually say a specific range right now. Okay, so turnarounds, I should put up here that represents max and min. All right, now this next function you know and love as, it's a subset of a polynomial. That's your linear function. And I think you guys know it better as y equals mx plus b. We're just trying to keep with some of the same notation. Remember that m is your slope. And to find slope, we do rise over run. So it doesn't matter which one you do first, so long as you are consistent. So if I start with the y value of a coordinate, then I should start with its same x value for that coordinate when I find it. And so then we know the domain is all real numbers, also because it's a polynomial. The range in this case for any linear is also all real numbers. And a subset of a linear function is the constant function, which would be, I'm going to just say f of x equals a. So if you just had y equals 3, or let's say -3, so I can draw it down here, that would be a constant function, which has a slope of 0. Okay, and I guess maybe I should include the special case. It is a line, but it doesn't have a slope. That would be this. So this would be the special case. Let's say if that was 2, x equals 2. That's also a linear function. All right, on to then, let's choose the parabola, which is the graph of a quadratic function. I know you spent a lot of time looking at quadratic functions and factoring them and solving them. And so you have different types of quadratic functions. What we have pictured here is an example of when A is positive. Remember, positive people smile, so that one looks like, put little eyes up here, it's smiling. And negative people frown, so this would be a representation of when A is less than 0. So then it's going down. Couple things that come up that are nice to remember with a quadratic is to find the vertex of your quadratic. It's opposite of b over 2a, which is actually the beginning of your quadratic formula, which is really helpful to know. And then you would take that x value, plug it in, and find the corresponding y value. So that would be the input, and the y value would be your output. The domain is always all real, and the range, it kind of depends again. So the range depends. If you are a smile, well, let's put it this way. You might have a maximum value. This would be if it's a frown, so y would be less than or equal to that maximum value. If it's a smile, then you have a minimum value. Your vertex is at the lowest point, so the range would be everything greater than or equal to that minimum value. And what else do we want to talk about? That's a quadratic, but remember you also have sort of we looked at a linear is first dimension, quadratic second dimension. You also have things like cubics that look like this. These are all types of polynomials. Quartic, which is what you had here. Quintic, which would be an odd function, so I have to be going in opposite direction. I hope I didn't 1, 2, 3, 4. No, okay, that was good. All right, so that'll start, and then we'll get into some more on the next page. So our first function here kind of looks like a line, and it is a line, but when it starts at the origin and stays in this first quadrant here, we actually call this direct variation. Now, it could go down here, but most real-world examples of direct variation tend to start in the first quadrant because you're comparing two quantities, and usually you don't have a negative quantity. So notice though you have no plus b. So it is a linear function with your y-intercept, shall I call it, or your b value is always going to be 0. So it doesn't have a different y-intercept. M is still your slope. It's basically just a subset of your line with b equaling 0. And we tend to, for real-world problems, we tend to limit the domain to be greater than or equal to 0, and we limit the range then to be also greater than or equal to 0, but that's as a real-world application. And then, because I switched these up, this is now going to be our, take a look at it. What do you think it is? A b to the x, where your exponent is x. Hopefully you recognize this as an exponential function. Remember that exponentials, I don't want to stress you out, are the inverse of logs, but that will come later, okay? But here's what an exponential function. So if it is exponential growth, that means you're coming up like this. And if it is exponential decay, notice that here we are assuming in this one that x is going to be positive value. So that's why we're only looking at the b, because remember, if your exponent's negative, things switch. So here we have an example of exponential decay, which means then the b value is going to be between 0 and 1. It'll be like a fraction, 1/2 to the x. So if you're constantly taking 1/2 of something, you're getting smaller and smaller and smaller. All right, so it is a constant raised to a variable. So x is the exponent. Your y-intercept is easy to find. Remember, to find a y-intercept, you let x be 0. Anything to the 0 power is 1. So your y-intercept is going to equal a. And yeah, that's all I'm going to say about it right now. I guess I can say if a is negative, then you have exactly the same graph, and we will talk about transformations a lot later. The graph would reflect over the x-axis. Okay? Now let's get into our power functions and subsets of power functions. So a power function. Here we go. This one, and people, how do I go back in? Power function, there we go. People often get the exponential and power function, so you really want to make sure you got this straight. Think of a power function like x squared, x cubed, raising something to a power, to an exponent, as opposed to when your exponent is the variable, then that's an exponential function. All right, so power function. Now again, these two graphs are showing everything just in the first quadrant. It does not have to be in the first quadrant. If we're looking at, again, real world examples, where let's say you're looking at time as a variable, well, time is never going to be negative, so we tend to keep things in the first quadrant. Here's what the power function would look like if the exponent is positive. This is what the exponent would look like if it is negative. So power function is sort of, you could say, a subset of the polynomial, but it's just that one term. We don't have the several variables, so it's just f of x equals ax to the b. There's no other terms. Now let's get into a subset of that, and we're going to have to draw these graphs in here, so let me go ahead and do those. This one we are going to call inverse variation. Now, inverse variation is, notice, like your power function, a times x, but now that exponent, if you write it on one line, is a negative number. So you actually have a ratio, a over x to the n. And what that does is it means you're going to always have an asymptote. Remember, that's sort of like a border, a line that your graph will not cross. So in inverse variation, y equals 0 will always be a horizontal asymptote. I'm always going to abbreviate it as HA, H-A. All right, so let's look at the different types you might have. If a is a positive number, so your numerator is positive, but you have an odd degree. Think about 1 over x. What would 1 over x look like? It would look like this. It would have a graph. And in this case, actually, you also have a vertical asymptote. This is, again, a parent function, so no transformations. X equals 0 would be your vertical asymptote. So that would also be a border. So we have vertical asymptotes here. All right, so an example might be like 1 over x. Now, if I suddenly made a negative, but did like negative 1 over x, what that does, it's basically a reflection, and it doesn't matter whether you say over the x or the y, because it would work both ways, and it would look like that. Now, what if a is positive back, but now it's even? So for instance, something like 1 over x squared. Well, since you've squared it, it makes all the y values positive, so it's going to, both branches are going to be up here. And if a is negative, that again, now that's a reflection over your x-axis, and that would look like that. All right, so this is, again, special case of your power function. And obviously x is never going to equal 0 because that would just be crazy. And you have the x and the y-axis as your asymptotes. But then we get to our last one here that we're going to talk about. Even though in your notes there'll be more, but that's what we're going to cover in class. So in this video, this last one is your rational algebraic function. It's kind of a long name. So this one is a polynomial over a polynomial. Obviously, q of x cannot equal 0 because you can't divide by 0. And so this one is going to have two different asymptotes depending on what your transformation is. So notice here, this is a horizontal asymptote, which has been shifted away from the x-axis, and here is a vertical asymptote that's been shifted away from the y-axis. So we have different cases. This would be, well, it's going to be hard to talk about things being positive or negative. We're going to look at these and figure out how do you know. I do know in this next one, probably something's going to be even overall. But basically, these are examples that you will see. And on this one here, notice it looks like a line. You're like, what happened? And we will investigate why that is. But when you just have a hole, that's an example of a removable discontinuity. I actually like this word better, discontinuity. And I usually abbreviate it with RD. I know some teachers just call it a hole in your graph, but I like the idea of removable discontinuity because we're going to be looking at how do you find like vertical asymptotes, horizontal asymptotes, and removable discontinuities in class. All right, see you next time we meet.